hear anything. Huh? Weird. Usually it says recording in progress. Assisting your seems pretty weird. All right, so you're recording. Not hearing anything. Turn up the volume. Okay. If I knew, I did turn up the room volume. Is that AI telling me not hearing anything? It would answer if it was AI, I guess. Possible. I don't really know how to change the volume here. It's probably in this thing. Anyway, I guess it's running. Um, anyway, so next week I'm not going to be here on Wednesday and I can't do a live Zoom thing. So I'm going to record it and like put it up maybe this weekend. I'm like preemptively thinking what I'm going to do on Monday. It's a little tricky, but so sorry about that. But I got this thing came up and I got to like go. I'll be back on Friday and I'll probably have a second, like this homework's up and I'll put another homework up for whatever is going to happen on Monday and Wednesday for the following Friday. So I'll try to get everything stacked up by Sunday. Yeah. So hopefully it'll be okay. Anyway, so any questions or anything or right. So anyway, so we've been looking at chain conformation, this business. So oops, there. This is from this paper by Colby. So Colby's at Penn State. He's kind of a well-known guy, especially in solution polymer stuff and polyelectrolytes and sulfonated polystyrene for battery membrane type stuff. So he's done quite a bit. Anyway, so he just shows this picture in this paper. It's like a general overview of what for linear polymers, kind of what long-range interactions can lead to. Right. So if you have polyelectrolyte, you can have basically a straight rod structure. Conjugated polymers like Kevlar, would be like that too. It's basically a straight line is a possibility. And then the thing that most people are interested, or the kind of the books are written about, are the theta state. So this random walk, which follows Brownian. There's a lot of math that goes along with that, Gaussian statistics. And then if you make that more real by adding in excluded volume, kind of like the van der Waal concept, then you get this good solvent coil. Then the thing that biologists are interested is in this collapse coil, which is like a folded protein. And also this can occur in a certain region of the phase diagram where you have a dilute polymer. So if you look at that phase diagram, so this thing somewhere down here. The phase, so there's a region where you can go below so this is a two-phase region at the bottom and an in solution above. So it's for a particular molecular weight polymer in a solvent. So because of polymers, so it's not symmetric about composition because the polymer's got a molecular weight of like 10,000, which shifts the phase diagram to the left. So this is in the kind of 1% region. So you have a critical point, and then this normal, so this kind of U-shaped thing is a Hildebrand form of mixing of something with something else. So it would be normally symmetric, but because of the mismatch in molecular weight, it shifts over. Then you get this other, so one issue is it's shifted over. One issue is it depends on the molecular weight. So this critical point will follow the dotted line up to the point where you have an infinite molecular weight, and then you reach the actual theta temperature for the phase separation, which is where chi equals 1/2 from the equation we had for solution thing. Anyway, so we'll talk more about this later, but basically there's a spot where you also have this issue that the polymer will act is an independent structure, and beyond that, when it's isolated, so when you're in dilute, the concentration within the polymer can't change. You can't dilute it. You can put more solvent in, but it won't rip the chain apart. So it's still got that composition that it floats around with, like a little balloon of solution. So once you reach that point, then you have independent coils. So they're going to phase separate at that temperature as you cool it down, like you precipitate out salt or sugar and water as you cool it down. So you reach that point, it's going to phase separate, and it doesn't matter what the composition is. So if you go to, say, infinitely dilute, so you just have one chain, it's going to just phase separate. So just make a collapsed coil. It'll just shrink down to nothing, to just a 3D object. So that's called the expanded to collapse coil transition, right? So it's kind of a region where you could do that conceptually and also experimentally, and also people say that this is what happens when a protein folds, kind of. The difference is, and for the paper next week, which I've already looked at, so the protein isn't isolated. You know, in fact, when it's in your body, the proteins are in a concentrated solution. So saying that this has anything to do with protein folding is a little odd, because actually you're way out here. You're concentrated. So it isn't in that region. But nonetheless, due to the specific interactions of the protein, they do fold like that. And people use the theory of polymer collapse to describe protein folding. So we'll see, like, you can get kind of two kinds of folding. One is a step change in folding, which have an enthalpy like a melting or a crystallization kind of thing. And the other is like more like a glass transition where it doesn't have an enthalpy, where it just kind of happens, right? So, and you can, in the theory that we have now can predict both of those. So the kind of just folding is what's happening here. Like this doesn't involve an enthalpy of transition going to this collapse state. And the other one is more enthalpically driven. So it's got an enthalpy of transition. Anyway, so this has loosely to do with this paper. Yeah.
Temperature, no matter the concentration, it is because phase separation happens.
Right, because once you get below the overlap concentration, the concentration doesn't change because you have a balloon going around, which is your polymer, and it's at fixed concentration. No matter how much solvent I put in, it's going to have the same composition, C star. If you look at one mirror of the chain, and within the neighborhood of that one mirror of the chain, the composition is fixed, right? Unless you rip the chain apart, which you can't do. I mean, you can do it if you light it on fire, but basically you can't do it without lighting it on fire. It's basically, you're stuck at that composition, no matter how dilute you make it. In that case, it can't phase separate into like water and oil. It's got to make little nano particles collapse. So that's called a single molecule nanoparticle. So people are making single molecule nanoparticles for whatever reason. I mean, drug delivery is always the catchphrase that people are going to say, you know, but you could, I don't know, you could probably use it for something, you know. So you can make just the idea that you can make a single molecule nanoparticle is kind of interesting. And then the use of it, who knows? It's like, anyway, you can imagine that people come up with schemes about what to do with it. But so anyway, that happens, right? All right, if you go, anyway, so this isn't about that. This is about 2D polymers, which is graphene oxides, the main candidate for that. So if you take graphite and you take Scotch tape and you put Scotch tape on graphite and rip it off, you get graphene, you get a single layer of carbon. So the guys at University of Manchester discovered that. There were two guys, they won the Nobel Prize for Scotch tape and graphite, which is basically like a pencil and stuff on your desk. Yeah. So, I mean, more or less, but basically that's what happened. And then there's other ways to make graphene. You can put graphite into like high acidity and it'll attack. So graphite is like aromatic rings. So they make a planar structure because they're conjugated. There's just going to have a bunch of hexagonal I can draw a hexagon. It's gonna have two things. It's just like that thing forever. And then these are all double, single, double. So if it's conjugated, so if they're conjugated, they can flip. Right, so they can go like that. It means they have to be in a plane to do that. So that means this entire thing has to be a sheet up to like meters. And this is basically 5 angstrom, right? So it's over a huge size range. It should be a straight sheet. But it isn't. All right, so the problem with this is it doesn't, you can't put it into solvent, so you can't do anything with it. And if you put it into more and more concentrated, it makes graphite again. They stack up because you have pi bonding between the aromatic rings. They just like associate up, right? So you get multi-layer things coming from it that aren't exactly, they're useful, but they aren't exactly as useful as a single layer, because a single layer, this has like conductivity. If you dope it, you can get conductivity across this conjugation. You have a 2D conductive sheet. And if you can do chemistry to it, you could make a computer from it or something with a molecular scale elements in it. So, I mean, it's possible you could do some things with this. Thermal conductivity is good in one direction, not in the other. That would make it good for thermoelectric devices, say. You know, we need to have conductivity in one direction, not the other. Thermal. So, I mean, there's a bunch of things you could do with it. But it doesn't solve anything. So you can, what you can do when you make this by the solution route with acid, you end up with like some hydroxyl groups and some hydroxyls and carbonyl groups sticking off that are polar, right? So del negative. So those will mix with a solvent, like a polar solvent. So that's good. So that's called graphene oxide, right? And that kind of becomes some of this easier to work with, but it isn't as conductive because you lose the conjugation. And then when it loses the conjugation, it loses the planarity. So transitions could happen. So you could have transitions like sheet to crumpled, right? And you could have crumpled to 3D. So this is like coil collapse. This is like, maybe that's like self-avoiding walk, and maybe this is like Gaussian, or I don't know. So you don't know, these things aren't exactly analogies, but there's some kind of linking together of these. Sorry, this thing does that. Yeah, all right, so that's this. So there's people have looked at this, you know. There's a review article. So I put that here. This is from the review article, but oh, is it up? Sorry, thanks. Reject. All right, so this is what our story is. We got a chain. It can go to self-avoiding walk, it can be Gaussian. It can do things like polyelectrolyte, and those can make helical structures like DNA, double helix, and then you can make polymer crystals, aligned crystals, amorphous, whatever. So this is kind of what's known. Then this is like, well, these things are also polymers, or they're 2D polymers. So you could say you can make a crumpled sheet, and then you can make like then this idea that they could fold. So, or they could like self-assemble into like bed sheets that are folded up. And then the amount of folding, they could ripple, they can make tubing or cones. So you start to get this imagination starts to take hold, and you can go anywhere with it, right? So you can do crazy things. And then you can also make stuff with it, right? So the idea is like, how does that happen? So that's what they're trying to search through here in this paper. This is like this year, October or something, I think, but so it's kind of good. These guys are at Jinling University in Changchun, China. So China's got, I think there's like 45 cities, over 10 million people. So places like this are probably like bigger than New York City. We have never heard of it, you know? So it's kind of a weird thing, you know? So most of the people in the world are living there, and they're living in these giant cities, in my impression. So it's kind of like up to us to figure something out, like a connection with them. But anyway, nowadays, most of the journals are being edited in China, you know, the science journals, and most of the papers, because of the financing, the way China finances science, so they're mostly Chinese are trying to publish like crazy. So there's a lot of stuff going on. it's loosely sometimes linked to US, but anyway, becoming more and more like on their own, or Europe, but anyway, so that said, so they're studying this problem. So they go through a little bit of the history of it, which I sketched out a little bit here, what they say, which is kind of, since it gives them context for what they're doing. Anyway, so a guy named Cantor, so we have the gems. He's like Nobel laureate. And then Cantor was a guy that worked pretty closely with him. Anyway, he started this kind of sheet study before graphene was discovered. So he was doing sheets before. There's also carbon disulfide is another sheet structure. So there's molybdenum something, sulfur something that's also a sheet structure. So there's many, not just graphene is a sheet structure. There's other things, and some of these can be used as catalysts and catalyst supports and things. So there is a whole group of materials that are sheet, and then clay. Like clay is also a layered structure that has sheet. So there's a variety of materials that can be. Those are like oxides, kind of complicated aluminum, aluminosilicate oxides of clay. They'll make kind of complex structures, and they're ionic. So these things are non-ionic, these are ionic, and then graphene's non-ionic. So those make things a little bit different. But anyway, so Cantor was interested in this because he's sitting around with coffee in France. Like that's what they do. They think about sheets and things. So he had nothing to do with that. So then the idea is like you have this sheet. So Cantor got this idea that L was the parameter of interest. But if you talk about like the molecular weight, that's L squared. Right. And then if you want to talk about the size of the thing should go with squared should go with n. That'd be like df equals 2. And then d min is going to be 1 and c equals 2. So it's a 2D object that's perfectly flat, makes a two-dimensional object that follows that kind of scaling law. L goes with n. So he's talking about, he proposes in Cantor 1, he says Rg goes with ln of L to the 1/2. So like, and then the paper just says that. So what is that? That's like Rg squared goes with ln of L. Then that means that you have L is exponential of Rg squared over something. Something's like in L squared. That's our Gaussian chain rule. That's like what we've had for Gaussian chain. So he says, he just pops out Rg goes at L to the 1/2. It's kind of comes back to the Gaussian chain equation, except written so you wouldn't recognize it, I guess. Right. Anyway, so because L is n squared. Anyway, it works out like that. So anyway, that's Cantor 1 thing. Then Cantor, this is what he says is a straight flat sheet. Then in Cantor 2, he had self-avoidance. So he has a self-avoiding walk for a sheet. So he says Rg goes with L to the nu, and he says nu equals 0.8, which is the number that we got. If you talk about Rg goes with n to the nu is 0.8 for self-avoiding walk. So he likes the number 1.8, which is 8 over 10 or 4/5. Right, and L is n squared. So anyway, you end up with that. If it's a 2D object, it ends up that nu is 1 by d min, which means how crumpled it is. So this is for a self-avoiding walk. It gets a crumpled sheet, and then d min is 5/4. Right. So, and then that means it's df. df is c times d min, and that ends up giving you 2.5. Right, and they call that that's kind of the Cantor-Flory. He's using the Flory theory. He's doing the scaling thing. This df is 2.5 for the crumpled sheet. So it's more, as you crumple it, the dimension goes up of the thing. Right, so it's a little messy. It's even messier because he isn't using n, he's using L. And he doesn't have this context of saying like the object is a two-dimensional, the fractal dimension, and then how crumpled it is. Like he doesn't have it broken down into that. He has just this new number, which is kind of the crumpled number, if it's a 2D sheet. Once it collapses, once it collapses, then D min is still 1 and C and DF are 3. Becomes a 3D object. So C is what the object is. Once it collapses, it's not a sheet anymore. So C goes to 3. And that transition is sharp, the transition from sheet to crumpled. So far, like Cantor 2, they haven't seen crumpled, they've just seen self-avoiding walk. This is 1979, by the way. And then so I'm just going through because he goes through this in the beginning. Then he goes through, then they have the idea like, well, if you're thinking about a model of this, then you have this kind of bending constant for bending these things. And then they also throw in like a spring constant. So basically, once you put in a bending constant to it, then they can go to fold. You can have this thing kind of fold, and the K decides how easy it is to fold. So low K, if you have low K, it folds. And if you have high K, it's flat. That's 1987. This is all pretty old. And then a guy named Bohl comes along, and he does simulations of hexagonal, so kind of like graphene or benzene stuff. And then that's page 1 of 3 here. But anyway, so with this, he does simulations, and he kind of gets 3D objects from it. So it seems to be kind of useless, this Bohl thing. But what he does is he comes out with the idea. He does a simulation. He can get RG as a tensor. So you have some object oddly shaped, and then you can say like, what's the RG in each direction? What's this kind of the size and the average size in each direction? Then I can make a tensor of that in whatever coordinate system I have. So it's got 9 numbers for 3D, and then of that tensor, you can diagonalize it, so you can find the eigenvalues, which are going to be if you have like a rectangle. So you could rotate that rectangle to any coordinate system, and then you take a random RG in each of those 3 directions, right? And then that would give you a tensor for RG. If you diagonalize it and find the eigenvalues for that, those would be like the thickness of it in these 2 directions, like the major numbers that you would want to know, like if it's a sheet, what's its thickness and what are the 2 lateral dimensions. So because they're in the computer simulation, the objects are floating around in any direction, then they just analyze it and get this tensor of the RG in 3D. Then they have to diagonalize it and get the eigenvectors to say what the thing is, because they don't have a way to quantify what it is, right? So they get Cantor, this Bohl guy invented this approach, I guess, to get these eigenvalues, and then those would be like 3 would be the thickness, and then 1 and 2 are the lateral things. Okay, so this brings up this kind of thing. So the thing has a volume, and then that volume is going to equal like lambda 1, lambda 2, lambda 3, right? So that's a invariant. It's an invariant of a tensor, like the volume doesn't change. So there's like 3 invariants for a 3D tensor, I think. I don't remember tensor math that well, but anyway, one of the invariants is the volume, which means that lambda 3 has to go with like 1 over, or lambda 1 times lambda 2 has to be equal to 1 over lambda 3 if the volume's fixed. And when you're going through this folding thing, I mean, assumingly the volume's kind of fixed to the object that you have, like you aren't increasing, decreasing volume. So that brings us back to the paper. So in the end conclusion of this paper said he has some crazy function that relates, so he calls it L1, L2, lambda 1, lambda 2, or L1, L2. And then there's some other symbol he uses for it, but if it's got 1, 2, 3, it's lambda. It's these eigenvectors. So you expect lambda 1, lambda 2 to go with 1 over lambda 3, meaning that it should kind of decay down like that. Like, in other words, if lambda 3 gets larger, then 1 over lambda 3 has to get smaller. Then this thing should drop down if it's at constant volume. That's kind of check number 1 that tells you there's something screwy about going on here, I think, I mean, even if you didn't have constant volume, you would expect it to drop, but his equation, which you can't understand exactly how he gets to, this equation 7 shows it going up, So that's kind of rule number one here of sheets, you know, say like rules of sheets. I mean, some kind of like things you could touch base with somewhat, you know. For rule one, that didn't work out, you know. Rule two is that, so this thing called the Gibbs-Thompson equation, right? So it basically says that if you have some object like a nanoparticle and it's got some size r, then r is going to go with, and if it's a sheet, so the sheet has two surfaces, so it's going to be 2 times the surface tension of the sheet divided by the bulk enthalpy of the sheet. In other words, thermodynamically, what would be the size of the thing you get out, times the critical temperature for phase separation, and then you're at a lower temperature because your phase separating is a T. So basically the quench depth. So the bigger the quench depth, the smaller the thing you make. And then T, the phase separation point decides it. But basically the size should go with this surface energy by delta H. That's kind of how this should work. So in other words, if I change the surface energy, which he does in the simulation, so he's in his simulation, he's doing this. He's got a system of what he calls P and S. So like different kind of balls are of the same size 1. Like one's called B is 1, and the other one B is 1. So he takes his balls and he makes them into a grid, a 2D grid that's square, which is strange, you know, because the main thing you're looking at is this hexagonal thing. And when a guy did an MD simulation, so Bohl did an MD simulation of the hexagonal ones, he got that made like 3D when he put in potentials, which means it just collapses down automatically, right? He makes it square and he gets folded sheets, right? Like something kind of like when you fold sheets. So is it that he used squares to do this, that he got sheets instead of 3D or something? Like, does it matter like what shape he used? And the shape has nothing to do with any real 2D structures. It's kind of just odd that he picked that shape. And within the system, he has forces between the beads because of the thing. He's not using energies, he's using forces. And the forces he calls alpha. So he has alpha SS, alpha PP, and alpha PS. Okay, so and both of these are 25 kind of unitless because KT equals 1. So then units of KT, and KT is 1, so they're unitless. And then the alpha PS, he goes from 25 to 35, or 39, I think. All right, so when it's 25, all these things wash out and he gets a flat sheet. Right. These are forces that he uses in something called DPD simulation. And then when he gets to 30, 35 or something, it just forms a 3D. So 25, he gets 2D, 35, he gets 3D, and in between he gets this folding. The folding happens. You know, so it's kind of interesting. I mean, he's messing around with that. What's the point here? So the point is like this force PS is really related to the surface tension. That's like the surface of the PS can only happen at the surface of the thing. So the bigger alpha PS is, the bigger the surface tension is, which brings you back to this. That says that the larger surface tension you should get a larger kind of thickness for the thing. Lambda 3 should go up with the surface tension. And that's kind of what he gets from the that's what he gets. So you get, so alpha PS is that energy, 25 is where it's flat, and then this is getting kind of larger and larger force. So the surface tension is getting higher. Expect this lambda 3 to get higher when that gets higher. So when I think that works out here. This goes to higher surface, that gives higher lambda 3. So that's good. Like the direction is right for the surface energy. And it's kind of complicated derivation of this equation that's messy. Right? I mean, so the equation is like unreadable, but basically and ununderstandable kind of based on what he says. But you can say, like, look at it. Well, he's relating lambda 3. So So he's got lambda 3 squared to lambda 1, lambda 2. So you can think of those like y is 1, 2, and x is 3. So yeah, it relates those two. And the parameters it uses is this bending constant by the surface tension, the ratio, so they're coupled, so they don't separate. And this beta, which is beta is an aspect ratio of the structure. Like beta says, like, is it a sheet or is it a 3D object? Beta's got two choices, sheet or 3D object. Like 1.83 is 3D object and 2 is sheet for beta. So beta is just saying what it is. It kind of makes sense. Like those things are related by what they are and by the surface tension to bending ratio function. And A0 is the A0 is the original number. So that's A0 is a fixed number. It's L squared. Anyway, so anyway, so there's like three parameters that govern, and that's where he gets this line from, and it relates signal lambda 1, lambda 2 to lambda 3, but the trend is in the wrong direction from what you'd normally expect if you had a constant volume. And I mean, you'd expect it to decay, it increases. That kind of makes you wonder what's going on here. But it is kind of a phase diagram he gets out of this. So let's see. All right, so let's see. Anything else here? Let's see. I did number 2. Yeah, the other things that happen here. So Bull is kind of messed up, but he's doing electrodynamic simulations. That's useful. Right, and Bull's doing something called implicit solvent. And this guy's, the new thing he's doing is explicit. So implicit solvent means, well, I have my polymer, then I'm gonna have like the interaction between the beads, and then the solvent's kind of here, but basically I'm going to ignore the solvent. Like the polymer's in a vacuum, and I'm saying I can compensate for the solvent by just saying I change the interaction between the polymer and itself. So I ignore that there's a solvent there, because it's always going to be, you're always going to have like the energy of the solvent, energy of polymer, energy of polymer, solvent. And if you say like, I can get rid of the solvent, and then I can just kind of have these things compensate for it. Because in the end, you're looking at energy of solvent plus energy of solvent, polymer, minus 2 energy solvent polymer divided by 2. That's your average energy. And then that's going to give you the chi parameter, which is the number of coordination number, like 6. Times average energy over KT, that's per unit of the chain, right? So it's basically the delta E gives you chi, and this whole thing is just one number. So you can ignore the solvent in that, yeah. Because you want to know that the average energy, this is from Hildebrandt. Why is it minus, because you want to know the difference between, you're trying to look at phase separation. We have solvent, polymer, and then it's going to go to solvent polymer. So that you want to know the difference. You want to know the delta E in this thing. Because that's the average delta E. Difference between if they're mixed and not mixed. You're mixing like red and blue marbles. You want to know what it's like before their energy, before they're mixed, and then after they're mixed. So it's minus. So it's the unmixed one, SSPP, and then the mixed one, PS, and the difference is the difference energy. That's the chi. It's complicated, but so anyway, so it's minus. Anyway, so if you say that there's just one number chi, you can forget about solvent, right? Then you can just run the simulation with a chi, and bingo, you get the answer. That's implicit solvent. The advantage is that with that, you can use actual molecules in your simulation, because there's only the polymer. You don't have to worry about a gazillion solvent. So it's in dilute solution. There's like so many solvents. You have to keep track of every particle in it that's moving around, right? So basically, if you have to creep, the computational money you have to pay to make the simulation is going to be incredibly bad, right? So So there's two options. You can ignore the solvent and use implicit solvent, or you can change the simulation procedure you're doing to something that's super simple, like idiot simulation, you know? So you just use a linear, instead of using the expelled potential, you use like a linear relationship for the potentials. And you just make everything as simple as you possibly can. Then you just say, well, then I can account for the solvent. That's what DPD is. You're going to dumb down your simulation so that you could run it on your cell phone, right? Instead of a supercomputer. So that's what they're using here is DPD. So this is very popular. And all right, so you're going to use the same, you're going to use lamps to do molecular dynamics. If you use lamps and you use DFT, density functional theory, to get the atomic electron densities, so then you can have an actual molecule, you know, like the actual molecule with the actual densities of the electrons, add those up in a molecular dynamics simulation in lamps. It can spin for a while and it can give you 1 picosecond of whatever happened, you know. So, or you could say, like, forget about DFT, electronic cloud, forget about molecular anything. I'm just going to make it up as I go along and make up some equations that give me the answer that looks like reality, which is useful if you're at larger sizes where maybe some of that stuff doesn't matter and you just have balls moving around and whatever. So the answers agree with physics, you know, but the methods aren't really based on physics for this. So this paper is a review of DFT that he cites, you know, and then he's got this is his paper. What's this? That's not what I want. Maybe I didn't get it. So he's got also this supplemental where the first part of the supplemental is just describes DPD simulations. Again, the potentials between the things, that's not the right thing. Yeah, sorry. Get rid of that guy. Oh, it's right here, which I think I opened it, but yeah. So the first part of this, so the equations are just linear equations with a cutoff. So there's a linear, so there's a conservative force, which is like the particles repelling each other like a Lennard-Jones. The Lennard-Jones would have a minimum where they'd reach an average distance. This doesn't have any minimum, it's just a straight line. You know, so that's a much simpler computationally, like hundreds of times faster than a Lennard-Jones potential to work with. Then there's this dissipative and a random force. Random's like temperature and moving the things around, and dissipative like a drag force, like a viscosity to slow the things down. So you have a repulsive force, a drag force, and a random force is temperature. You add those three together, they're all linear, they're all the same functional form basically. One's squared and the other the other two are linear, right? So they're all the same thing. So actually this part of the calculation for all the forces you do once instead of separately more complicated equations. That's where you get the 100 times faster. See, everything's packaged into one thing that it all kind of packages together. It has nothing to do with reality, but I mean, kind of has loosely to do with reality. But basically, with this, you can put in all the solvent. You know, so it's a simplified thing. This guy, was it Grote and Warren? This is like a gazillion citations. Like everybody. Anyway, there's some interesting stories about these characters, but they're not repeatable exactly. But anyway, so what else is in here? So anyway, that's what he's using in this, the DPD. I ask you to kind of go through it. So look through what he did in the supplemental. And then if it's too confusing, go back to this review article. Then I think you can find a wiki page on DPD because it's popular. So you can probably find someone that describes it simple enough that you can figure out what's going on with it. But it's popular, so you should just have a rough idea what it is, you know. And so he's repeating that. All right, so this is how he calculates RG. This is like page 2. Yeah, so that's how he calculates RG. Then he runs a simulation for these different energy forces of interaction. So you have the force, you don't have the energy. So if you wanted to say, say you wanted to calculate chi, which I asked you to do. Well, these things. Sorry. So if you want to get chi for the system, like between the chi between that thing and the solvent, you need to have like the energy, solvent, energy, polymer, energy, polymer solvent. And then that thing to get the average energy so you can get the chi. And you also need KT, but he says that's 1. In the supplemental, he says KT is 1. Delta E you can get from that if you have the energy. And Z, I guess, is 2 here. Right. So in other words, you have a sheet, you have a ball, it's got 2 places that interacts. I don't know, there's probably 2 is a good number to use. Then so you can calculate chi from his things if you can get energy from force. So I give you that equation here somewhere. So you have the forces, you can get the energy from this, like his alpha times this thing would give you the energy of interaction between the particles at some distance. So linear function, so it doesn't end. There isn't one fixed value. Rij equals 1 would be the diameter of his ball. So that's probably a good place to look. So you could just plug in 1 for that. RC is also 1, so everything's 1. So this thing just gives you some number before alpha, and then you can get the energy. Right. So once you have the energy, I think, somehow this thing gives you the alpha by 6 as the energy in units of KT, which is 1. He uses, so 1 for that. So then you can calculate chi from his numbers, which means you could calculate, I don't ask you to do that, but basically you could calculate the free energy of G by KT is going to be phi ln phi plus phi 1 minus phi ln 1 minus phi. Phi is the composition of your sheets, and then plus phi times 1 minus phi times chi. It's actually the Helmholtz free energy, but you can call it Gibbs. And then from that, you could plot as a function of composition G, and you get like single phase or 2 phase, it look like that. The binodals are there. So basically you could get the phase behavior of the system if you knew what the composition was, but he never gives the composition. So he just says it's a box with 3,000. It's 2,500. Let's see. It's square root of 25. It's like 50 beads for the sheet, and the box is 3 times the sheet size. I guess you could kind of figure out the concentration from that, yeah.
I want to know if DPD and MD are the same thing or they.
All right, he's using lamps. He's using the same program, but instead of putting in the Leonard-Jones potentials, he's putting in these linear potentials. And it's just a button you push in lamps. You say like DPD or like MD.
Both of them study the particle behavior of fluid.
Yeah, they use DPD all the time for polymers, because if you want to do explicit solvent, where you want to see the solvent molecules, then they go to that, because you can't do it otherwise. It would just, the computer would smoke. Yeah, so that's kind of just like a cheat to let you, so the computer doesn't burn, I guess, so yeah, so it's kind of like a simplified, like a dumbed down version of the other, but it makes it able to do other stuff. But yeah, it goes faster. It's faster, not better. The other one's probably better, but say like Leonard-Jones potential is already an approximation. It's not real, right? It's just an approximation for the energy of what it might look like, so it's all right, I guess, to do something else. And then Leonard-Jones at close distances is just a repulsive potential. So he kind of has this kind of same potential. It kind of looks like it a little bit. It's made up, but all of it is made up. It's just balls moving around in the end. So it's kind of all made up, but it kind of correlates with reality.
We'd like to practice more on that.
Yeah.
Working on something like that, probably.
Yeah, so I got a homework to do lamps thing, like to introduce into lamps, that we can do, probably later on, I guess. I don't know. I could give it to you now. You could do it, but basically it's not hard to do. You just download the stuff. You can run it on your laptop. You know, the beginning part you can run on your laptop, and then if you want it to make more complicated, you go and you can get time on the supercomputer in Ohio for free. So you can get 2,000 hours or some crazy amount, you know. So it's plenty to do whatever you want to do. So yeah, you can just play around with it like a hobby that can turn into a job. So people like to hire you because like when they hire someone that's doing experiments, they have to give them like 5 million bucks to set up a lab. When they hire a guy that's doing simulations, they have to give him a 110 outlet. Right? That's it. So basically you can work in the library, you know, and then just you ship everything to the supercomputer. So all the machinery is somewhere Ohio State, and you just sit here and type, you know, and then do analysis like this. So it's kind of sweet. I mean, companies like it too. So it's like kind of a good thing to do, but it's not for everybody, you know. At some point, you got to touch reality. Like you can easily get lost in the cyberspace with this thing, you know. Start really. I mean, people you can get so far into it that you don't even know like what day it is or something, you know. So it's a little bit like an addiction. Um, anyway, so that's what they're doing here. Yeah.
Paper.
On the what is it again?
Paper.
On the paper? All right. Okay.
Yeah, the image. The film. Yes. I heard you were modeling graphene sheets.
That's a good point. Yeah, that's one of the questions in the homework. Like, why did they choose a square grid? And does the square grid have something to do with what they get out, which is square sheets folded in squares? Like everything's pretty square here except for that one. It's like if they had done hexagonal, would they still get square sheets? Like that isn't answered. And when the guy Bole did hexagonals, he just got crumpled out. He just got a collapsed sheets from it. He didn't get any folding. So yeah, that's a good question. Is like, why is he using this thing instead of something that would be closer? And his solvent are the little dots here. So they look like nothing, but each one of those dots you have to keep track of, right? Over billions of steps. So that adds up. Like if you try to do that with the lamp, with the molecular dynamics, that's what cooks the computer because the sheet is pretty simple, right? So anyway, so yeah.
Some saying effect equation. I really don't understand how did it come into play?
Well, it does, he doesn't mention it in here, but basically it says, the Gibbs-Thompson says that the thickness of the sheet is going to be proportional to the surface area. And this alpha PS is the surface area. And as he increases alpha PS, the thickness gets thicker. So it follows, it should be proportional, in fact. So this should be proportional to that. So it kind of looks like that's what's happening. I mean, you know, there's a lot of error bars again here, but basically it seems to go in that trend. So that part checks out. The part that doesn't check out is like this thing should go with 1 over that, and it actually goes kind of up instead of down. That doesn't seem to be right, you know. If it's constant volume, this has to go down. Right? And the volume in this process of the sheet doesn't seem to really change much. I mean, it might change a little bit, but if it increased, I think it would make it go down more. You know, so I think it wouldn't have the effect that he's showing. Anyway, so see what else I got here. So then he mentions this flopple. I've never heard of this before, so it's kind of worth looking at if it's something you haven't. So flopple von Karman number, which it turns out it's like has to do with how sheets fold, you know. Oops, where did it go here? That's what I want. Why am I article? This doesn't look like, anyway, there's a Wikipedia page for it that doesn't seem to work here. FL, I think it's called OOPLE von Karman. Something like that. Nope. Carmen's some kind of Broadway show. Anyway, I see. It's because it's that weird, the weird symbol. Got it. All right. Anyway, you can get that if you want, but basically, I don't think it goes anywhere. It's just about how sheet things fold. Probably not worth talking about. It isn't a question on the thing. So he calculates RG, gets the tensor, finds the eigenvalues, and then it's all Q is an eigenvalue function. It's like lambda 1 plus lambda 2 over L. So it tells you how folded it is. Like lambda 1 originally is L. So this is 2 originally, and then it goes to some other numbers. It's 2 when it's fully expanded. And then as it folds, it's kind of a folding number. So anyway, he's got folded things, and he finds out he has these six regimes. One's at large, so he's got basically the flat sheet, the folded sheet. He's got them listed here: double folded sheet, quadruple folded sheet, weird tube things, and then the crumpled state, the final collapse state of the thing. And he's mapping out that Q, seeing that it's a function of this alpha PS, and then he does different size sheets. So he's seeing these dependencies, and this is kind of a phase diagram in a sense, but he doesn't call this a phase diagram. He calls the other thing a phase diagram. And then what else is in here? These things, I don't think you have to go through, because all the rest of this section, I mean, you can go through it, see if you can get something from it. Basically, all the rest of this section gives him equation 7. So it's a short paper, that's the end, right? Gives him equation 7, and the 7 is what he calls the phase diagram. So how this is a phase diagram is a little screwy. I can ask you to kind of look at that. So the first thing is, what's DPD? So kind of just go through whatever I said and whatever you can garner from you can do a wiki page on DPD, I think. Like he's got this supplemental that describes it. There's a paper that I put up there. And I think if you put in like simulation, there's like a wiki page. So it's a popular thing. You could also look, like LAMPS probably describes it. Like they have a web page where they probably practicing DPD with LAMPS. LAMPS has like everything, and it'll have the code written, you can just plug it in, so it's kind of like, so that hopefully that won't be too bad. There's one issue, like he's coarse graining, so his idea is he's collecting a bunch of molecules and putting them together into one bead. But the sheet, like a graphene sheet, is 1 atom thick, 1 carbon thick, right? So how can he coarse grain if it's a 1 atom thick thing? Like he's coarse graining in 3D when it doesn't coarse grain in one of the directions. So the whole coarse graining idea here maybe needs to be rethought, I think. It's not exactly right to coarse grain and pack it up as if it's so thick, right? I mean, anyway, that seemed to be a problem to me. Anyway, the parameter nu. So nu is the scaling coefficient that he gets that relates L to the RG, right? And then you can figure out from nu what these other dimensions are, like d min, df, and c, because L squared is n, and RG to the power equals n. RG to the df is n. Right? So it turns out when you figure it out, if it's fixed 2, that c is 2 because it's a sheet, then 1 over nu is d min, this minimum dimension, and d min 1 over nu times 2 gives you df, until it gets to the collapse state, and then df is 3 and c is 3, and d min has to be 1 because it's a straight line through the structure to conduct electricity. So he gets this like pore solvent, and so you can calculate from these alphas what chi is. It's just an exercise to get chi from something else. Let's see, where is it? Oh, RC is the cutoff for a simulation. So he only does this force thing, this linear force. He only does it to a point. That's the other advantage of DPD. So the point is like 1.5 times the sphere size. So it's only over a little distance he calculates forces. Otherwise, you have to calculate force with every particle in the system. He's only kind of doing the next neighbor, and even only part of that. So RC is like half of the, that's why you end up with 1/6 here. RC is half of, it's 1.5 times RI, what the one, RC is a fixed number. It's like 1.5. This is in his supplemental, he gives these numbers. So, all right, so Z uses a parameter Q. That's the lambda1 plus lambda2 over L. And lambda1 L originally so it would be 2 originally, I guess. To explain the value of Q for each of the 6 classes. So when it collapses, you can figure out what Q is for collapsed and for folded. Like it'll become half of what it was for straight if it's folded type thing. Right. And then he says it's a phase diagram. So this is just like kind of whatever I said. And then so how do you use the phase diagram to predict phase behavior? I guess it's just a general question. I didn't mention that there's something screwed up with it, like it's going in the wrong direction, but anyway, and then so linear polymers, we have these states, then how does that compare? That's what I first said, like from that paper, like how do the things relate? Like we have this picture and then he has this picture. What's the link between them? And there might be no link. The collapse state is definitely a link. Like they both have a collapse state, right? So that's definitely ground zero of linking. Then the rest of it, like what's a flat sheet? Well, a flat sheet's almost like a polyelectrolyte, extended coil, extended chain, right? And then the crumpled chain is a little bit like a self-avoiding chain. In fact, when they add in self-avoidance, they get the crumpled sheet. So there's some linkage there. All of it is pretty vague, but just kind of, I think the point that there's a review paper in here where this came from, and then the point is like there's something the same between these things and there's some things that are quite a bit different, and just kind of philosophize about that. There's no right answer to E. It's just like think about it, figure out. Yeah. Collect, what is it? Yeah. That's when it crushes, like when a protein folds, that's a collapse state. Like the coils collapse down to just 3D. It's just a ball of goo, I guess, with no space in it, no solvent in it. The solvent's all excluded. It's just a ball of goo. We're out of time though, but so, right.